This lecture describes matrix operations and how you perform them in Excel and how they relate to problems and situations commonly encountered in chemical engineering. So the first circumstance in which matrix equations arise is systems of linear equations. So here we see a set of linear equations written three different ways. First, explicitly as a11x1 plus a12x2 plus etc. a1n xn equals b1, and then n such equations. So you have n equations and n unknowns. The coefficients of the x sub I, which are the variables to be found, are aij, and the right-hand sides are these b1 through bn. That can be written compactly as a matrix, capital A, dotted into a vector of unknowns. X equals a vector right-hand side b. An additional way of writing the same thing is to represent the matrix as a box of numbers, a matrix of numbers, an array of numbers. A11 through A1n is the first row, A21 through A2n is the second row, and so on. And that is then dotted into a column vector, x1 through xn, written downwards as a column, and the right-hand side is b1 through bn, written downwards as a column. The matrix multiplication, the multiplication of the matrix on the left there by the column vector on the right, the dot in the writing of a dot x, I visualize as literally taking the rows of the matrix A one by one and tipping them over so that they're vertical and smacking them up against the x1 through xn, multiplying the adjacent values and adding them up. And that is what happens in the equations, as you can see in the top line, a11 x1 plus a12 x2, etc., is exactly what you get if you do this. If you take that row there, a11 through a1n, and tip it over and smack it together with the x1 through xn, multiply the adjacent terms and add the whole thing up. And that gives you the first term on the right-hand side. So there are three different ways of writing linear equations, and it's useful to be able to go back and forth in different circumstances. So as I just described, the multiplication of a matrix times a vector is based on taking the dot product, the inner product as it's sometimes called, between the row of the matrix and the column vector. And that's what I was just describing in words a moment ago. So matrix equations are important in chemical engineering because they arise commonly in writing balance equations, in writing the equations that express the fact that what goes into a process must come out. It expresses the fact that everything winds up someplace. Everything is made of something, and the equations that express that are always linear type equations, and so solving these is an important operation to be able to do. So the inverse of a matrix allows us to solve linear equations, starting with a dot x equals b, where I haven't actually written the dot. If you could find a matrix A inverse such that when you multiply it times A on both sides, you multiply the vector AX times A inverse, and you multiply on the right A inverse times B, and the matrix A inverse has the property that when it multiplies the matrix A, you get the identity matrix. You see that on the left, it undoes the multiplication by A, because the identity matrix times X is just X, and then what you have is X equals A inverse B. And what you've done effectively is divided by the matrix, but the proper way to think about it is you've multiplied by its inverse, multiplied by the special matrix that gets rid of the matrix on the left-hand side. So we will see in Excel how to compute a matrix inverse or how to solve linear equations, and that I will demonstrate in the second part of this lecture. While we're talking about matrices and vectors and so forth, having introduced them in the context of linear equations, which are often balance equations, those matrices and lists of unknown variables and lists of right-hand sides don't have any particular geometric significance. They're just, a matrix is just a way of writing a set of linear equations. But in other contexts, vectors have a geometric significance. So a list of numbers v1, v2, v3 is sometimes a geometric object, for example a displacement vector, or is a displacement in the x and y and z directions, or a velocity vector is a rate of change of the position in the x and y and z directions. And so in some way the three values are not just a list of numbers but actually correspond to a physical thing, a physical concept. And then the dot product, which appeared in, for example, matrix multiplication, has a geometric meaning. It turns out, okay, if you have two displacement vectors or two vectors in this geometric sense, and you take A dot B, and you calculate it in the way where you take A1B1 plus A2B2 plus A3B3, as is indicated below. And so there's three ways of writing that dot product. A dot B, or I can write it as, a sum, AKBK, or I can write it out, A1B1 plus A2B2 plus A3B3, or I can write it as a row matrix smashed up against a column matrix, like one part of a matrix multiplication. All those are equivalent, okay? If you evaluate that thing, it turns out that the number you get is the same thing as the length of the vector A times the length of the vector B times the cosine of the angle in between. And the length of the vector means the square root of the sum of the squares of its elements, okay, by the Pythagorean theorem. That's what the length of A means. So the square root of A1 squared plus A2 squared plus A3 squared, that sort of thing. So this is somewhat magical, but this dot product has this geometric meaning of being related to the relative angle, the angle between the two vectors. Likewise, matrix multiplication has a geometric meaning whenever you're talking about vectors that have a geometric meaning. That is, for instance, there are matrices which have the effect of rotating a given vector about some point by some angle, or reflecting some vector about some plane, or stretching a vector in certain directions. Any kind of transformation like that that is linear, meaning if you doubled the vector, the answer would be doubled, or if you add two vectors and transform them, then the sum of the transformed thing is the sum of the things transformed. All those operations can be represented by matrices. And if you applied more than one of those operations in turn, then the effect would be the same as the product of the matrices acting on the vector. So that's just a little bit of background about other instances in which matrices and vectors appear, which are not in balance equations, but where the vectors are geometrical things. And you will possibly encounter that kind of thing in other parts of chemical engineering, possibly fluid mechanics, for instance, or other circumstances. Civil engineers deal with this kind of stuff a lot. Chemical engineers somewhat less, but sometimes. So now I'm going to demonstrate how you perform various matrix operations in Excel, including adding a constant to a matrix, adding two matrices, multiplying two matrices in the matrix multiplication sense that we described before, taking the inverse, taking the determinant, multiplying a matrix times a vector. So here is a matrix A that I've typed in here, a 2 by 2 matrix, just as a simple example. And so first I'm going to just add a constant to this matrix. To every element I'm going to add 2. So the way you do that is simply make a little formula in here which is 2 plus this element of A, and hit return, and then take that formula and copy it into the cells that are the same size, so to speak, as the original matrix. And Excel automatically copies the formulas with incrementing the row and column indices so that the successive elements of A likewise get 2 added to them. So you can see 1 plus 2 is 3, 2 plus 2 is 4, 3 plus 2 is 5, 1 plus 2 is 3, right? So next we're going to add two matrices, and that proceeds similarly. So in here we're going to have the sum of the matrix A and B. So that's equal to the first element of A plus the first element of B. And then again we take that formula and we copy it into the successive cells. And again Excel increments the row and column indices when it does the paste, so that the successive elements of A and B wind up getting added together and put into this little box. So multiplying two matrices proceeds differently because it's not just a simple cell-by-cell operation. So the way that that's done is similar to the use of the function linest that we encountered in doing linear least squares fits with confidence intervals. We first highlight the region in which the product of the two matrices will go. Then we start typing a formula. We don't click into this box. We need this whole thing to be highlighted. And we start typing equals. And the function for multiplying two matrices is called mmult, matrix multiplication. So M-M-U-L-T. And then parenthesis, and then it prompts you for what it wants, which is a specification of the two arrays that you're going to multiply. So the first one we get by highlighting the entire set of cells for the matrix A, and then comma, and then we highlight the entire set of cells for the matrix B, and you can see that there's the color coding that tells you, what you've highlighted and what's going into the equation. And then parenthesis, and you don't hit return at this point, but instead you do the same thing as was done to execute linest. It's Command Shift, hold those down, and then hit return. And when you do that, you get the matrix product A times B. In a similar fashion, we compute the inverse of the matrix A. So we highlight the region into which the inverse will go. We start an equation with equals, and the function to invert a matrix is called minverse, matrix inverse. Parenthesis, and then it prompts us for the array that we're going to invert, the matrix that we're going to invert, in other words, and we highlight the entire thing. Parenthesis, and again, don't hit return, but hold down Command and Shift, and then hit return. And we get the inverse of the matrix. We can verify that that is the matrix inverse of A by multiplying it back onto A, and we should get the identity matrix. To check that, we're going to do a matrix multiplication here. So equals mmult, parenthesis, of A inverse times A. Close parenthesis, again hold down Command and Shift, and then return. And indeed we get the identity matrix, which verifies that this is in fact the inverse of that. Finally, if we want to multiply a matrix times a vector, okay, so I've got this column vector v, which is 1, 2, and I want to multiply a times v, that's also an instance of mmult. So equals mmult the matrix A, comma, and then you highlight the vector v, okay, which is a column vector. It needs to be a column vector for this to make sense, and of course it needs to have the same number of elements as the rows in A. So then close parenthesis, Command Shift, return, and I get the product. One final operation that is sometimes important to perform on a matrix is to take its determinant, and that is done with a function called mdeterm. So that's equal to mdeterm. This is just an ordinary function, meaning I don't need Command Shift return. It's only filling in one little square, but I need to highlight the entire array that I'm taking the determinant of. And then I just hit return in the ordinary fashion, and I get the determinant of that matrix. So those are the various operations on matrices and vectors that are commonly performed in Excel. Now we're going to use them in solving a tiny little 210 style problem having to do with some mass balance equations. So mass balance equations are typically going to be a system of linear equations, and so here's two equations in two unknowns. Here's two different ways of writing it. I can either write out the equations for M1 and M2, or I can write it in a matrix form. So the coefficient of M1 in this first equation is 1, and the coefficient of M2 in the first equation is 1, and the right-hand side in the first equation is 100. And the coefficient of M1 in the second equation is 0.2, and the coefficient of M2 in the second equation is 0.95, and the right-hand side is 30. So first I'm just going to type out the numbers here for the matrix, right, which should be 1, 1, 0.2, 0.95, and the right-hand side vector, which for some reason I've called D, 100 and 30. And then I need to compute the matrix inverse. And so we did that before. That's using the function minverse equals minverse, parenthesis, highlight the matrix you're trying to invert, close parenthesis, Command Shift, held down, and then return. To get the solution of the equation, I multiply the matrix inverse times both sides. That eliminates the matrix on this side, and of course multiplies the right-hand side by m inverse. So the answer, therefore, will be a matrix multiplication of m inverse times this right-hand side. So that's, I'm going to put that here. I've already made a little label for the answer, and that again is a matrix multiplication using mmult. And then first factor is the matrix inverse, and the second factor is the right-hand side. Close parenthesis, Command Shift, return. To check the solution, I can multiply the matrix, the original matrix, times the solution that I have, and I should get back the right-hand side. And that's going to give me a vector, so I highlight a region in which to do this multiplication. I use mmult to do it. The first factor is the matrix, the second factor is the vector right-hand side, Command Shift, return, and I get back the original right-hand side.